I really should get into the habit of doing Alt R to do that. But yeah, Monday, lab 10, right? Lab 10. Okay. Let's get started. Share screen. And 3, 2, 1. Okay, so if I remember correctly, there are 3 problems for this week. One of them is a cakewalk, and I use the word walk with the utmost pun intended. This one is pretty straightforward, so I think we can do 2 out of 3 of these. So technically we'll do like 1 and 2. How about? We'll do most of them. So the first one is like doing Taylor series for sine, and then there's going to be 2 different ways you're going to do it. And that's the first. So the first 2 parts is one method. The parts 3 and 4 are going to be the other method. No, I'm sorry. The part 3 is like the second method, and then part 4 is like comparing their accuracy. And I forget what table lookup is trying to do, but oh yeah, this is like the whole sine table that you would see that big old printout of like, oh, these are these different sine values. And this, I believe, is going to be just like a, not so much coding, but like the whole reading a table or something like that. So that's like a format sort of thing. We can go through, yeah, we'll go through this one. Lagrange polynomials, this is like, I think we've discussed this in the lecture, where like you're given a bunch of points, and then you're like, what's the lowest order polynomial that you'll need to like kind of loop through all of those? So that's going to be like the number of, or that's going to be of order the number of points minus 1. So like if there's 4 points, you'll need like order 3. You'll need no, right? Yeah, you don't need a cubic for that. Yeah. Yeah, okay, yeah, that's right. And then there's only, that's a 1-parter. Okay, well, I think the best place to start would be 1. Let me stop sharing, and there's something in the chat. Post document only has 2 questions. Oh, what did they remove? I assume they removed 3, right? Oh, did they email us about that?
Yeah, I think they removed one of the questions in order to include the 0th part.
Oh, that makes sense. Okay, when did they send that? I want to make sure that I'm like looking at the. Wait, did they tell us that? Okay, you know what? Let me just make sure that I'll just use the one from the B courses.
Yeah, I'm trying to find the email, but it's
I
there
don't think
somewhere.
They didn't tell us, right? I think they just said, oh, lab 0 is for this week. Okay, found it. Lab 10 PDF. Let me just download this one. Okay. Sine's still here. Lagrange is still here. No gate. Okay. Makes sense to me. Okay. In that case, I guess we will. Okay, let's see. How are we gonna do this? So there's only 2. So then I guess like since it's a 5-parter for the first one, we'll do 2, and then maybe we'll show like we'll do the full solutions for like parts 4 and 5. How about that? I think 5 was like relatively complex, and then 4, no, like let me just look at 4. Okay, okay, part 1's okay, part 2's okay. Now, look, let's do 1.3, 1.5, and Lagrange. Let's do that. The other ones are pretty straightforward. Let's do that. Okay, just to summarize. So full solutions 2, I'm typing in chat, 1.3, 1.5, and 2. There we go. Oh, and since we're not doing the problem 3 that was from my previous document, my amazing pun has gone to complete waste. So let's open up MATLAB and see what is on the table for this week. Okay, this is like 4 lines. I can't count. 5 lines if you can include end functions. So I'll just kind of show the skeleton code for this one. It's like you're given a. Hold on, what is this? You're given like a. Is this a matrix or is it? Let me just make sure. Okay, it's a 2D array. And it's M by P. So it's an arbitrary number of rows and an arbitrary number of columns. And you're trying to compute the Taylor series about 0, aka the Maclaurin series. And they give an image of this in the actual PDF of like x minus x to the power of 3 over 3 factorial, et cetera, et cetera. And okay, it's just you're trying to compute the nth order Taylor series of sine of each of those numbers in the matrix. So it's just you'll have a matrix of like 1, 2, 3, 4, 5, 6, and then you'll need to be able to take the sine of all of these. But it's not going to be the exact sine. It's going to be the nth Taylor approximation of sine. So it's going to be slightly different than if you just took like sine of each of these values. But you can find what this actually is in the PDF, the sine, the Taylor expansion of sine. Give me 1 second. Let me actually set up my drawing pad so that it doesn't, my S's don't look like that. There we go. Okay. That is part 1, relatively straightforward. Keeping Taylor convergence. This doesn't look like much of the skeleton code, but like all this information is in the PDF. Like, this is literally stated in the input, well, in the output table. So is this one, and this is basically the error. Whatever your sine series is, aka the output of your initial mySine function, and compare that to the actual sine of x. So let me clear this in 3, 2, 1. So this over here is going to be, you're going to start from, as stated in the PDF, n pi over 2 dot 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 n pi over 2. How big this vector is going to depend on what your n is. And the increments are going to be, I'll use this to specify increments, pi over 8. That's what this means. Here's the start, here's the end. And then your sine series, you're going to calculate an approximation of sine using your mySine function. That's this one over here. And then the error, all that is how different are your results versus the actual results. That's the error. And then the next term that you're going to want to compare, well, I'll leave that to you to check. Annotate, clearing in 3, 2, 1. All right. Here is 1.3. So here, let's do this one out. How about? So we're going to try and improve on our mySine. So spoiler alert, our mySine is not going to be completely accurate. That's kind of the point of 1.2 over here. So this one, we're going to want to make some modifications so that when we're further away from from the origin, then a certain value, that's going to be 2 pi actually, then we want to kind of shave that off and then kind of return to part of the origin. If you look in the PDF, it'll say something like, well, you'll want to have sine of x plus or minus 2 pi to be equal to sine of x. If you're like taking sine of 3x, sine of 3 pi, then you're going to kind of shave off 2 pi and then bring it back down to like sine of pi. Okay. Now, here's the question I want to pose to you. All right. So here's the general structure. You want to loop over the number of elements in X. And should this be, well, we already know that this is going to be like between, so this is the range in which we're going to operate. Negative pi to pi. Let's draw a number line. Sine operates in this range. You may have seen this from like a previous math class. Sine of x operates in this region. So if you draw that out on like a Cartesian coordinates, that'll be from here all the way to here. Here's pi, aka negative pi. Okay. Now, is this a less than or a less than or equal to? And explain why you think that's correct. I'm fielding that question to the crowd, by the way.
Sorry, I don't really understand what it's asking. So, like the range of the sine function, is it from negative pi to pi? Or...
The purpose of this range is this. Here's the range in which we operate. And if we fall outside of it, let's say our x is, let me use a different color actually. X equals 3 pi. We're outside the range. We're like way over here. So we want to bring x back into a realm of operation. So here's x equals 3 pi, and then we want to shave off like 2 pi from that. Okay, now we're over here at pi. So what I want to say is this. Once we hit pi, right? Let's say our x is pi. This is our new x. Are we okay with this? Or do we want to do something else with it? Like, I mean, in this case, we would do, so I'm looking at this loop right over here. Kind of skipping ahead, but it's the same structure. If we're shaving off 2 pi, and let's say we have this as like greater than, or let's do greater than or equal to. Greater than or equal to. So this is going to continue this, and it's going to shave off another 2 pi, and it's going to land over here.
Well, so it depends on which loop comes first. I'm going to say that if it's, say, right, so if it's 3 pi, you'd want it to, I think it'd be better off just like having it stop there. And then if it's negative pi, you want it to be greater than only. So negative pi, you want to loop up to pi, just so that you don't have to hold duplicate values for like negative pi and pi. So for the first one, I would do like greater than, and then for the last one, I would do less than or equal, or
wait, right, less than or less than or
greater equals? Sorry, greater than or equals.
So this, so
that way this, that way negative pi always maps to
So just to confirm, you want this to be less than and this to be greater than equal to? I just want to confirm.
Yeah, that works too. Because then pi will just, so then if you input pi, then it'll just map down to negative pi, but you already have a value for negative pi, so it's fine.
Yeah, I think, let's see.
I don't think it really matters. Like, I mean, you can have a value for negative pi and a value for pi. But if you want to like kind of be more elegant about it, then you would avoid duplicate values by having pi mapped down to negative pi, and then.
I
Yeah.
think if we did this, it would avoid us. It would like avoid a while loop, and it would still be okay. I mean, unless I'm missing something in the PDF that just prevents us from doing that.
But I think if you just put pi,
Oh wait, actually,
then you would end up with negative pi,
wait, there is some. Sorry,
which
there
is
is
fine.
there is
but
something in the
it
PDF
depends on
that
the concept,
says.
fine.
So there is something in the PDF that says that one of them is correct. So it's under the description for the output. So it has closed brackets. I didn't see that before, but I think if it didn't tell us that, it would be okay to do either one. But this would need to be one or the other. So if it's closed brackets, what would it need to be? Tell me.
So basically, if you look at the description for the variable sim periodic, it says value of sine computed at every radian value of x by converting into the range of negative pi through pi inclusively. It includes both of them. So what does this tell us for the transformation we need to do here for those two loops? Sorry, I interrupted you.
Then both of them could just be less than or equal to or greater than or equal to. Sorry, less than and greater than. So because you don't need, because if it's equal,
That's
then
right.
you don't need to shift it up.
That's right. That's right. If it's equal to either negative pi or pi, that's okay. We don't need to modify it. I want to follow this up with another question, because I believe that it's very important for us to always keep in mind that when we're making a program for something, when we're coding something, we're trying to solve a specific problem. So why exactly do you think we are bringing everything outside the negative pi to pi range into that range?
Check the PDF if you're not sure, by the way.
What is the what for bringing it to the negative pi to pi range?
Yeah, why are we doing that?
Yeah. My question is, if we have a point over here, why do we need to bring it to this range?
Because
same
the
above.
Taylor series is inaccurate the further away you get from the
Exactly.
point that you're measuring from.
Exactly. So you are making use of the fact that you know that the actual function is periodic. So you know that if you subtract 2 pi, then the sign of that value of that number will be the same, but you are close to the 0 point where the Taylor series is accurate. It's a very good answer.
I'm going to write that down because it's a very good point. Solution diverges far from x equals 0. This is why we're doing this whole 1.3 business. Thank you, Jose. And thank you, Yuhang. Okay, let's do this officially and put in a less than. If it's less than negative pi or greater than pi. All right. So this is just doing the same thing, only we guarantee that our x is going to be within this range of negative pi and pi. It's just a modification, but it's going to do a lot, hopefully. Okay, this one here, if I can get rid of this in 3, 2, 1. Okay. Now we're going to do something pretty similar to 1. Okay, yeah, this is similar to 1.2. We have a, so this is a little bit funky, but I'll tell you what this means. This is an anonymous function. Have we gone over anonymous functions in this class yet? I'm just wondering.
I think so, but I think it's a bit awkward with MATLAB because you need a function handle every time pass the function in.
Gotcha.
You actually don't always need a function handle. I wonder if I don't think we would have an example of that right now, but maybe I can show you guys how to use anonymous functions without a function handle in the app designer tutorial later on.
It was just like, I think I was trying to create a higher order function. So a function that outputs another function, and then it was kind of throwing a tantrum when I tried to use that function, and then I had to like add the @ symbol, and then it worked. Essentially, I was like,
Oh, okay.
yeah.
Yeah, it gets tricky. There are some situations where you don't really need the handle, but it's tricky. Using a handle is always easier.
Thanks. Oh, give me 1 second. I need to check something. Give me like 15 seconds. Okay. All right, so this F0 over here, what it does is first of all, here's your function, right? What we're going to do with this is we're going to try and find, if we plot it on, say, a graph, we're going to want to find where that hits the x-axis. That is, like, where's the root? So F0 is going to take this f of x that we have and say, hey, where's it going to hit 0? And that's going to be some angle. Some angle of here is going to, and what this says is this: the error between our guess, our sine periodic that we did in 1.3 versus the actual value of sine, we're going to compare these, and what angle is going to give us like the, if I'm reading this correctly, it's, when is this going to give us a perfect, like a perfect match, right? If this is 0 and then, no, wait, hold on. No, not perfect match. This, when is this going to be equal to, the tolerance? Where's the eraser? So when does this like stop being an adequate approximation of sine of x? That's what that's saying. So like, if we, this is like a kind of number line within this range, let's say like -2 and 2. I don't know what these values actually are, and that's kind of why we're doing this problem. Within this range, then that value, I'm going to write like scribble minus scribble, is less than the tolerance. It's within the tolerance. Within this range, then it's going to be okay. Outside this range, it's going to be, the error is going to be very, very great. Greater than tolerance. And we're going to want to try and find where that value is. So let's say here. So if the absolute value, if the absolute value of that angle is greater than some value, we're going to say, hey, angle equals infinity. And what we're going to do with that, kind of jumping ahead a little bit, is we're going to say the range of accuracy is going to be between, let's say this is infinity, between negative infinity and positive infinity. If this is great enough, if this absolute angle is great enough, that means that this is basically accurate everywhere. Okay, here's my question to you. What do we want this value to be? The absolute value of this angle. Remember how, like, here's my hint. Remember how we're defining our periodic sine, right? So under what condition, what angle does this need to be if for our sine periodic to always work? Remember our realm of operation. I'm going to get this part out of the way. I'm going to check the, sorry?
It's greater than, or it's greater than pi.
Right. If this is greater than pi, that means we're not concerned about it. Our sine periodic only takes values that are between negative pi and pi. So if this is true, if the inaccuracy threshold angle is greater than pi, then that means that sine periodic is always good enough. All right, let me get rid of this. 3, 2, 1. And oh, I accidentally did that. That's fine. We'll still do sine lookup. Okay. This one's a little bit more involved, but we can go through it. Let me check the chat. Yeah, people are answering. Okay, let me stop for any questions so far. How are people doing on problem 1? Typical silence says people are okay. You can type any questions in the chat as well. Okay, let's review what sine lookup's trying to do. You're given some, they call it an m by n double. So it's going to be some number of rows, some number of columns. And table's going to be p by 2. So it's going to be 2 columns of unknown length. And that's going to be taken from your sine lookup. And that's going to be like an Excel file. So first column, okay. I'm not gonna, here, let's just share that while we're reading it. I want to make sure people understand. So let's draw this out, shall we? Here's 2 columns, column 1, column 2. First one's degrees, and the second one is value of sine at that angle. So let's say we have like 30 degrees, 45 degrees, 60 degrees, and here's going to be sine of 30. It's not going to say sine 30, it's going to be like 1 divided by 2. It's going to be like 0.5. For example, here's going to be 1 divided by root 2. That's like 0.7071. That's going to be, you get the point. And it's going to be an entire column of data. And it only goes from negative 180 to 180 degrees. So remember the domain of sine. Negative 180 degrees, 180, aka negative pi to pi in radians. And then this periodicity of sine will hence refer to 1.3. And it's going to return the value of sine at each angle. So we're going to use, what this is doing is we're going to have a table that computes, without looking at the code, I'm guessing it's going to use our 1.3 function. And it's going to use that to calculate, it's going to do the same thing as like we were trying to do earlier, but with our sine periodic. And you take a matrix and compute a bunch of sines. All right, let's go back to the MATLAB, shall we? And clear this. Let's go to new share, MATLAB. Okay, angles and values. So these are nothing more than the columns we were shown earlier. Column 1, column 2. So this is what's going to come out of this is our table. Call this table. And we'll shelve X for now, but like this first part is just kind of slicing this table in half and saying, you go to tab ang, table angles. And this one's going to be table values. Abbreviated, of course. Now here's the first chunk. And what this is doing is nothing more than what we kind of did with our, like here they didn't actually use like my periodic directly, but hold on a second. They're doing X. So, okay, here's the thing you have to be careful with. This is given in degrees, these angles. So whereas X is given in radians. So this over here still dwells in radians, but it's like, I'll write C1.3. So it's still in radians. I'm gonna leave this as skeleton code, but like I'll let you guys figure out like what if you can how to do it using the mod function. There's a way to do it that's more elegant but more clever. You need to be a little bit more creative. So this one right here, don't neglect it. You'll need to convert all of these x's into degrees to match the table. And here we're going to want to loop over. Let's see what they're trying to do here. I said it's a skeleton code. And let me try and remember what we're trying to do here. I don't quite remember. I made a skeleton code.
Isn't
But
it
I want
supposed
to.
to be interpolation of like the?
Yeah, let's see. Oh, okay, yeah. Yeah, because it gives us like it gives us a discrete angles. Hold on, give me like 10 seconds. I need to like remind myself. Remind myself as in like bold dissolutions. Whoops. No one saw that. Okay, let me stop share. This is gonna need me to open something in MATLAB.
Yeah,
This
I'm looking at
was
it too.
I just don't understand how you linearly interpolate a sine function. Then that
the way what we're doing is this. Okay, before I should. Here's what we're trying to do. Like when we're trying to do linear interpolation, remember like the 30 and like 45 kind of thing. Let's say we know what this is. Like this is 0.5, 0.7. I'll abbreviate that. Let's say this is our table, but let's say we want something that's like 37 degrees. Now that's not part of the table, so we'll need to linearly interpolate. So we'll need to do like, okay, here's 30, here's 45, here's 0.5, here's 0.7. What's this like middle value right here? 37, and this is question mark. That's the idea behind like the interpolation, because this table's not going to give us the exact value. And obviously, like it's not linear, right?
So is it literally just connecting the dots, essentially?
Literally, yeah. Here's the
Okay,
sine thing.
that's not
We know
bad.
this, we know this. Obviously, it's not going to be
And-
like exact, right? There's going to be some discrepancy, but it's close.
And to answer your question, this is very commonly done in many engineering applications where, let me share a whiteboard to illustrate this, where there is some very complex function very complex, sometimes empirical function relating to quantities, I don't know, this happens a lot in hydraulics, related quantities that govern fluid behavior. It happens a lot in transportation. So you will have some design code where you're given some input, let's call it x, and the output f of x, and you don't really know what the function looks like. And in the case of the sine function, we do know how the function looks like, and we know it's non-linear, and we know many ways to calculate it through Taylor series, and I think there are a couple of other more efficient algorithms to calculate it. So we have many ways to calculate the sine function. But for many empirical relations, you just have some values here. If the input is 1, the output is 37. If the input is 2, the output is 39. If the input is 3, it's 35.5, and so on. And you don't really know what the function looks like because it's some empirical relation that we don't have a proper way to mathematically describe it. And let's say you have an input of 2.5. You know that this function is not linear. If it was linear, it would be easy to describe, and we wouldn't need tables to look it up. But what would you do if you had this input, or even 2.1 or something like that? So the best thing that you can do is interpolate between these two numbers, and you know it's not 100% accurate, but it's your best option. So this is kind of trying to replicate that kind of problem. Let me stop my share. There we go.
Thank you, Jose. Jose actually bought me some time to look at the solution, so I understand what we're doing right now. Yeah, Jose, do you want to look at Ava's part 0?
Sure. Let's go to a breakout room while you stay here.
Thanks. Okay. Here's what we're gonna do. I'll do this first part, but I'll kind of draw it while we're doing inside the actual for loop because it's pretty involved. So we're going to loop over X, and we're trying to. So I mean, here's the way they did it. Size of X size of X comma 1, size of X comma 2. This one, it didn't matter whether we remembered which is rows, which is columns. We're going to loop over the entire thing anyway. But this is rows. I'll just write rows, and this is going to be columns. Okay, here's what we're going to do. I'll type it out. Find the lowest angle that is less than X. And just a reminder, we did convert radians to degrees, so we know those are the same. So this is a valid comparison. What I want to do is this. I'll have 4 different. I want to find 4 different things, first of all. The low angle, and then the low value, the high angle, and then the high value. Here's why I want to do that. Remember the table from before. 30, 45, sine of 30. Let's just write it out. 0.5, 0.707. The way we interpolate, let's say 37, right, is we're going to take this as our low angle. I'll write this as low angle. Here's our high angle. Here's your high val. Here's your low val. What we're going to do is this. Think of this as kind of like an XY table. And these are like 2 points on our graph. Here's 30. Here's 45. I know people probably are somewhat okay with this, but I want to make sure that we have a conceptual understanding of what's going on side by side with this. Here's the sine. Here's, yeah, we're going to linearly interpolate, let's say 37 degrees. So the way we want to do this, I know I want low angle, but here's a technique that I recommend to make sure that all of these are at the same point. So I'm thinking about how to show this without like giving away the answer and like fielding some questions. Here, well, we're going to start with x of p comma q. It's going to be some value of x. Here's the x matrix. And then we're going to pick some value of this, and we're going to pull this out as xp comma q. Now, this is, we're going to want to check this over here, and we're going to want to compare a bunch of different values, right? I mean, this is not just 30, 45. This is like, negative 180, and then 30, 45. How do we pull out this one? How do we say, okay, here's 37, right? Here's 37 degrees. Here's our x. Here's our tab ang. How do we find the lowest of these that's less than our x? Like the greatest value that's less than x. That's what I'm gonna ask. What function do I need, first of all? So I'm saying min. You're close. We're trying to look at the minimum value or the maximum value that is less than 37. Yeah, the maximum value. Here's what we're going to try and do. We're going to find the maximum value of the table angles that in which the value of table angle is less than, less than or x. We could, here's the format we're using. The maximum of, I'll read this out loud. The maximum value of the maximum angle in which that satisfies the condition, the angle is less than x. So what, like, if you're curious, this right over here, this is going to be like the entire table, like cover this up. It's just going to be the values that are less than 37. It's going to like cover up anything that's above that. And it's going to take the maximum of that. Here's the maximum value. This over here is going to be your 30. This over here is going to be like the index. Let's say this is like, I don't know, the 22nd. That doesn't say 22nd. whatever. 22th index. Or just 22. Now, we're going to use this index to identify what the value is at that particular angle, and then what's like the next increment above that. I want to erase all of this, but I'll erase this part. So keep the graph over there. Now looking at this, we want the other three quantities we want are going to depend on what this index is. So low value. Off. All right. Which of these are we going to use? We're not going to use angle. We're going to use the values, right? So table values, and we're going to want index. We're going to do something similar for this one. Let's do high value first. So how we're going to find, it's going to involve table of values, but what's going to be high value? It's going to involve index, but what do we need to do to index to get that high value?
I'm sorry, when you in the comment, isn't it find highest angle that is less than x?
Yes, highest, so maximum value that is less than x. So maximum value of the maximum angle that is less than x. Did I do
doesn't it
something?
mean that find highest angle that is less than x in the comments? I'm just talking like I'm just
Oh, I
talking
see.
about the yeah.
Whoops, that's why someone said min. I have misled you. Sorry, Angelo. Yeah, the lowest angle is less than x is just the lowest angle.
So then high val is just just index plus one, right? The
Index
one
plus
after
one.
that.
Yeah. Thank you for the catch, by the way. This is always a good idea, except when it's not. The semicolon. Highest angle. Now this is going to be, well, kind of gave it away already. Table angle, what's this one?
Plus one.
Okay. We have our four values. So what do we want to do with these? This is going to involve some linear interpolation. And here's how we do that. Remember the slope intercept, no, not slope intercept, point slope form. M equals x2 minus x1 over x. No, sorry, this should be y2, y1 minus over x2 minus x1. And what this is going to tell us is this. We're going to want to find some point between them. And we can either start from up here, or down here. We can always, let's do the lower one. So I know my point here. So what I can do is this. I can draw a triangle. And I can say, like, I don't know what this one is, but I can say this. The value of our sine of 37 degrees, let's say, like sine of 37 degrees. Well, that's going to be equal to the sine of 30 degrees, right? That's this 0.5 over here, plus some question mark. And that question mark, we can say, using linear interpolation, is equal to sine 30 plus, we'll need the slope over here. So we'll say m multiplied by the distance between 37 and 30. So let's say like 37 minus 30. So how do we find this y2 minus, so y2 minus y1, x2 minus x1? We're not going to use like this distance over here, obviously. We're going to assume that the slope from here to here is the same as the slope from here to here. And we're going to calculate m as like 45 minus 30 over, I keep making that mistake. This should be on the denominator. 45 minus 30. And then this is going to be 0.707 minus 0.5. So we're going to approximate the angle. And then we're going to insert that into here. And then we're going to want, yeah, that's going to be your m. And that's, yeah, all of those are known quantities. And we can use that to approximate what sine is at 37 degrees. Now, all of that is something we'll need to put into code. Let me check the chat, actually. Let me see. Oh, sorry. Didn't see anything. So, sine table is going to be something. And we're going to want to say, let's calculate the slope first, actually. I'll say m. M equals, so here's going to be our, so I'll do this as a kind of like a template, y2 minus y1 divided by x2 minus x1. Now, let me get this out of the way. And say, I want my slope to be, so our y2, that's going to be our high val or angle. Well, it's going to be the sine at that angle. So it's going to be high val minus the low val. And then similar thing down here, high angle minus the low angle. That's our m. That's our slope. And we'll say sine table is going to be, okay, sine of 30. That is the value at our lower value. So that's low angle, no, low val, plus, we know we're m, and we want to find, okay, what is our 37? What value represents our 37 degrees? It's not going to be like high, low, val, or angle. What do we put there? Well, this is going to be, by the way, low angle. What goes in this blank over here? What do we need? Where's our 37 come from? X. Should I put X here? Does this look right to you people? Or do we need to do something? X is a matrix, right? Well, how do we get a scalar out of that? I'll give you a hint. This should be B comma Q.
X P Q comma Q.
Right. Since we're looping over the entire thing. So here's our P, here's our Q. So we'll do this for each and every single value of X. Got rid of too much. Okay. Let's see if this is going to work.
So there's no real reason that X is two-dimensional, right? It could just be one-dimensional and it wouldn't make a difference.
Or X. What do you mean one-dimensional?
Like it could just be 1 times M or M times 1. And as long as you just
Like
iterate through each of it.
vector. I think you're right.
Yeah, this could easily be like 2, this could be 1. Doesn't matter.
Okay.
It just, so long as we loop over the entire thing.
No, I think his question was meant towards here X is a matrix, but it could as well be a vector. And yes, it
Well,
could.
yeah. Because a vector is basically like a matrix with one of its dimensions equal to 1.
Mm-hmm.
And the scalar is just a vector with all of its dimensions equal to 1. Okay. Let's see. Oh, my Lagrange. Okay. Are people good in this problem, or should I move on? I'll leave this part as an exercise. I'll dangle that in front of you guys. Okay. We'll move on to my Lagrange. I'll try and pick the pace a little bit, actually. I'll clear this in 3, 2, 1. Let's do my Lagrange. Okay. Let's draw this out. Let's do a really simple example, ... What's the lowest order polynomial that passes through those? It's going to be a parabola. So 3 points, order 2. I have 4 points, ... What's the lowest order Lagrange polynomial that passes through all those? Like this, like this, like this. That is a cubic. 4 points. Order is 3. You catch my drift? We're going to want to calculate n up here, first of all. That's the number of points. But the way we're going to define our polynomial is it's going to take n, and it's going to subtract 1 and make that the highest degree. So it kind of hints at you like this, like a naught ... a n minus 1 times x to the power of n minus 1. So it's going to look in less kind of stretched out way. A naught plus a1x ... a sub n minus 1 x to the power of n minus 1. And we're going to want to find what these are eventually. These coefficients are going to depend on what points we're given. Okay, and matrix over here. So here's the first part. What goes in this blank, I wonder? Okay, so start at I equals 2. I see. We'll have our matrix. I'll draw it down here, but like, know this corresponds to line 12. We're going to want to kind of start from the constant and then work our way up to the highest degree. So we know this is going to be like a column of 1s. The reason we start at 2 is that we don't need to start at the first one because we already know this is 1s. We're going to first initialize it as like a bunch of 1s, like 1, 1, 1, 1, 1, 1, 1, 1. And then we're going to fill this in as like their actual numbers. That's the plan. Okay, so we'll start at 2, aka the x term. And then we're going to fill in whatever that matrix is. So x values from x data. Okay. So as a reminder for what we're trying to do, I'm going to write one more thing over here on the right. And that's the a naught, a1, ... an minus 1. And then we're going to want to here are the coefficients. And then we're going to want to say, here are our y values. So y, let's say y1, y2, ... y n. Yeah, it's not n-1 because we start at 1. So the way we're going to do this is we're going to want this to be x1 squared ... x n minus, no, x1. Let me clear that up a little bit. x1 to the power of n minus 1. These should match up. The n minus 1, the an minus 1. As stated up here. This corresponds to this last row over here. This is the final column, and then each element in that column is a different x. So that's this x data over here. Okay, we have a column of x data, and we're going to want to see this. So matrix, let's just go through the logic of this. Here's the second column what we're trying to look at right here in this first iteration. Matrix, all of the rows in that column, in the second column, is equal to, it's going to be something in x data. Well, we don't need to do anything to that. Let's just pull out the first one. X to the power of, well, actually, no, we don't need, it's just x data. Yeah, x data. But we want to make sure this works for all the columns. So what we're trying to do? Well, we're going to take this to the n to the power of 1 power. X data dot, I'm going to make a deliberate mistake here, n minus 1. Well, actually, is this a mistake? X data.
Shouldn't it be I?
Yeah, I minus 1, sorry. X data, is that a column or a, sorry, let me just check, or someone can tell me whether x is n by 1. Okay, it's already a column, so we only need to transpose it. Column vector. Okay, so this is fine. I was going to say, like, if this was like a row vector, we would need to transpose it. But for now, this is like, yeah, 2 minus 1, that works out to the power of 1, x to the power of 1. Yeah, okay. Thank you for that correction. So this is, yes?
Wouldn't it be like, shouldn't it be like what does it mean when you say, like, because like the left side is a colon, right? So that means it's the entire row is just equal to that one value.
But all of the rows in that column. So what this means is this: you'll do like 1, 2, 3, 4, 5, 6. You'll do like matrix 1, comma I, 2, comma I, 3, comma I. And this is the row index. It's like the row number, but like you're saying all the rows. You're scanning this way, and then you're saying column 2. So all this boils down to is the ith column.
Okay, yeah, I get it. You're replacing that whole column at once, essentially,
right?
With it,
as opposed to like
corresponding data points from the x data. Okay.
Yeah. All right. This looks good. We're populating the matrix. For each column, find the x values from x data. Okay, works for me. Dot, by the way, is required because, well, we can't really do this because that's illegal by matrix/vector operations. Dimensionality. Now, for this part, we're going to want to do another for loop, and we're going to want to start with a, interesting. So this part I'm not as familiar with, so I'll need to take a look at the PDF. What are we trying to do here? So first of all, we're going to have this coefficient be something like matrix. We're going to want to do like matrix backslash. It's going to be like an A backslash B. And let me see if this is y basis. Does this need to be? Actually, Jose, can you help me out with this? Like, what is this y basis stuff we're trying to do?
Yeah, let me take a look.
Oh, it's a second data point under a bullet point under details.
Let me look.
Here's what I'm looking at. Let me pull up the PDF. It's this one over here. There's multiple approaches, but what the solution does is this. You're going to have a data set that's, you have x1. So all of these are going to be like x1, x2, dot, dot, dot. And then at some x, that's set at some like value I, it's going to be 1. And the rest of them are going to be zeros, all the way up to x to the power of m, which is like the last one. So what this is going to turn into is a, like, let's say we have our matrix, and then we have our like coefficients a naught dot 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 a n minus 1 equals like 0, 0 dot 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 1 dot 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 0. Am I understanding this correctly?
Let me see. We'll have the set of data at the left, and it should equal, yes, I think, yes, that's the case.
Okay, the way they do it in solutions is this. They have this as, okay, they're setting the y basis equal to 1, and all the rest of them are going to be equals to 0. So they'll do, okay, so this equation that I kind of showed earlier with, like, here's your matrix, like here's the 1 dot 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 dot, and here's like the x1 to the power of 2 dot dot dot. Here's your a's. And this is going to change depending on which I we're looking at. Like this is going to be 0, 0, dot, 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 1, dot, 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 0. Hold on, but this is only for one of them. So, okay, I'm going to ask for 15 seconds while I verify this next part, because I want to make sure I get this right. Okay. Okay, gotcha. So let me share again. So this should be, yeah, it is the matrix that we were looking at earlier. So matrix and A's equals y basis of whatever that is. No, sorry, this is not y basis colon dot dot dot. It's just y basis. So this is going to be y basis. And okay, one thing we'll need to do. This is, so remember how Yuhang was asking earlier about the colon comma I. This is I comma colon, which means it's going to be a row. Now this operation over here, this returns a, it's going to be a column, but we need a row. So we'll need to transpose it into, so there's a few ways to do transpose, but like this is the way that you can do it. Find the transpose of that. Okay. This is going to be, so the final row of the coefficient output matrix. Like this is after you've reached the end here. And what do they want for that, I wonder?
For which line?
Oh, this last one over here. So we've already looped over the entire Lagrange thing. So once we've done that, we'll need one more line over here to compute the coefficient. The final row, because our coefficient is going to be it's going to be an m by 1. So here's m, and then here's m plus 1. So where m is going to be the size of our x data, isn't it?
Isn't
Yeah.
it the size of the polynomial?
Well, let's see. There's like
No,
m
no.
and there's n.
Yeah, let me check which one's which.
So the output says, so the first row is basis polynomial. The last row is a complete Lagrange polynomial.
It's the number of data points, and it's the number of data points.
Okay. So that's going to be our final like A not A1. Wait, this should be N. This should be 2, I mean. So how do we determine that? Oh, okay. I'm not sure about this. Let's check something.
I'm looking at this solution right now, and I am a little baffled, actually.
There's something in the chat, yi coefficient I. Let's see, so that would be y data. So, wait, so it'll be y data I, wouldn't it? Okay, there would be an I in it. This is outside the loop. We would need y data, and then we would need to, okay, I think I know. Matrix backslash y data. And before I forget, this should be, because we already did our y basis, we'll need to use our y data in this last part. You can, Jose, can you verify this last part?
Yeah, that's correct. That is correct.
Okay. Sweet. All right. All right. Open this up to questions, I guess.
I'm still confused on exactly what we're solving for the coefficient. So each row is a polynomial essentially, and then we just go down and
Yeah. It's
okay.
Sorry, go ahead.
No, go ahead. I didn't really have anything else.
It's just the A naught, A1, A2, ... all the way up to like AN minus 1. It's the coefficients of the polynomial.
So that's like, so one row is, the first polynomial, and then the second one is the second polynomial, and the sum of all of them is the entire polynomial.
Is it the sum of all of them?
No, I don't think it's the sum of all of them. No, it's just a collection of m polynomials.
No, as in the Lagrange polynomial can be written as a polynomial made of the sum basis, such that so like it says the Lagrange polynomial is the sum of basis polynomials. So I think like each row is a basis polynomial, and the Lagrange is the sum. If you like if you added the matrix like together.
Let me see. Function.
I'm just looking at underneath too.
Yeah.
So I think what we solve for is the basis polynomials, right? I just want to make sure I understand the question.
Yeah, we were solving for the basis polynomials.
Okay, yeah, that makes
yeah.
sense now.
I was mistaken. Yep, that's absolutely right.
Where is? Ah, found it. So 216, right? Oh, I'm a little bit too far. Okay, I think I found the corresponding section in the book. Let's pull it up. Okay, they said 213 to 216 was on this. This is cubic, but it's no, sorry. Oh, sorry for 216. Here's Lagrange polynomial interpolation. And then the way they and when did they cover this actually? The basis method.
I remember seeing it in the lecture slides. But yeah.
Okay, if it's in a lecture, I guess. Yeah. Okay, refer to the lecture then. All right. I'm gonna stop share then. Should we stop for questions? Got about half an hour.
I was wondering, maybe it's just easiest if I send you like a screenshot of my completed lab 0. Would that be good for you?
Sure. How would you? Wait, send it how?
I could put it in the chat directly or email.
Can you just share the screen?
Yeah. Do you want me to do
Right.
that now?
Sure. Yeah.
Yeah.
With
You know what?
everybody?
I mean, there's no lab Wednesday, right? I don't think so because it's Veterans Day.
Yeah, that's right. I don't think we'll have a lab.
Should we have an optional lab just to kind of let people?
For answering questions, we could do that.
Okay. We would be volunteering to do that though.
That's
Okay, we'll do
that's
it.
fine for me.
I'll be bored that day anyway.
Thanks, guys.
Also, yeah, just share your screen with us. We just need to check that you completed that portion, and that's enough. You can also, I think, yeah, sending a screenshot would also help if you are not done yet.
Can you see my screen?
Oh, actually, let me stop recording.